out with the schedule, which I'll also post in the same thing. We don't have 5 groups in each one, so I think I'm skipping the NMR lab, which happens to be A for the first week, because organic chem needs, I don't know, I need to figure out which is the best day to skip it for that one. Yes, I made my heart earrings for those of you who came to the chem night.
Wait, what?
Missed out on the kids. We try to vary it a bit, depends on when we can make it too. But next one can be like Tuesday or Thursday. Yeah. Alright, one more thing about lab. It's become department policy that lab coats will be required for all labs. So you have to bring your lab coat to lab. Part of that is due to our sulfuric acid incident in Gen Chem last semester. You didn't hear about that. Someone was doused with concentrated sulfuric acid and had to go under the safety shower and go to the emergency room.
She was using the beret.
In response to that, we're now
And I
requiring
think she was
upper
wearing
division students to wear lab coats, and the Gen Chem students are wearing aprons.
I always did. I always wore a lab coat. I did. And frankly, with how gross mine got, I'm glad I did.
Let's go ahead and get started. OChem to review, we're going to go into our carbon 13 first. So the next two are going to be carbon 13 and proton NMR, nuclear magnetic resonance. Looking back at our electromagnetic spectrum, we've talked about the UV vis, we've talked about the IR. Now we're going to be talking about the region corresponding to the radio waves down here. Very low energy electromagnetic waves. I think I have this marked as the exact location. It's even further on the end here, so it's combining the microwaves and the radio, so we're looking somewhere in this region. And part of that is going to depend on what you're looking at, so whether you're looking at carbon or hydrogen, and how strong your magnet is. So we have what we call a 400 megahertz instrument, which means that we use 400 megahertz radio waves to look at proton. So if you had a different strength magnet, it would have a different wavelength of radio waves that it would be looking at. Then we also have carbon 13 we can look at. It uses a different wavelength because carbon 13 responds to different wavelengths of the radio waves, and so it's going to be 100 megahertz when you're looking at carbon 13. The instrument itself does all of that adjustment and calibration, so you don't have to do those changes, but you do need to know that we're looking at different wavelengths there. And what we're looking at is we're going to apply the magnetic field, that's the B sub 0, to your sample. And then we're going to cause the transitions in the spin flip. You can put radio waves on any sample, and it's going to be spin flipping all of the nuclei, so we're probably seeing that all the time since radio waves are kind of abundant in our society. But in order to be able to monitor what's happening, we have to apply a magnetic field so that we can actually align them all and then measure differences in those transitions. And so we apply the magnetic field, and then we irradiate it with the wavelength, and it excites some of them to the inverted, so it's not aligned with your magnetic field. And then we actually stop irradiating it, and we observe which ones emit. So it's not like our other UV viz and IR where we shine the light on it and we look and see what comes out at the other side. We irradiate it, we stop, and then we see what comes back out after that. And that gives us information on the types of atoms that we have in our sample. Now, we do have megahertz as our radio wave, and so we don't really want to be doing all of our units in megahertz. And so our chemical shift that we talked about, which is our delta, is going to be equal to our shift in hertz of our sample from TMS divided by the strength of the magnet, or the spectrometer frequency in megahertz. So note that we have our shift, which is going to be in hertz, versus the wavelength of light that we're looking at, which is in megahertz. And so if you divide a hertz by a megahertz, you're going to have 1 million hertz in 1 megahertz. And so we do this in parts per million. And that's where the ppm comes from. Now what we're measuring here is going to be the chemical environment of each of the atoms. Remember, our atoms are going to be in slightly different chemical environments based on what they're connected to. And so they are going to have slightly different chemical shifts, and that's what we're going to be interpreting. So what we call the chemical environment. On that?
Is it just one quotation mark?
Is there more?
Yes.
Is it like
Open-ended quotation. No, there's another one.
something I've never seen? Okay.
So we have our sample that gets put into the NMR, and so in terms of sample prep, we need to dilute our sample because it needs to, using straight sample is a little too concentrated, and so we need to dilute it, but we need our solvent that we dilute it in to not interfere with our signal. And so we try to use a deuterated solvent, meaning all of the hydrogens are replaced with deuteriums. And that will help us from seeing too much of the solvent, because if you use just a normal solvent, all you would see is one gigantic peak for your solvent, and you may have sample in there, but if you have, say, a milliliter of solvent and a drop of your sample, you're not going to see very big peaks for those, and it's not going to be easy to interpret. So if we use a deuterated one, it doesn't show up on the proton NMR because it's not the same nucleus that we're looking at, and so we get rid of that problem. So this wouldn't be there, and instead we would see just a little peak, and then we could actually see our signals and be able to interpret it. Except the lab you are going to do. So the lab you're going to do is actually going to be looking at a Red Bull sample, and Red Bull is dissolved in water, not deuterated water, and you're going to add a little bit of deuterium so that you can lock onto the signal, but you still are going to have a huge solvent signal. There is a technique that we irradiate all of that water sample, and we can get rid of that solvent, and that's what you'll do in the lab, so we don't see it. And you'll have step-by-step instructions on how to do that. So there are ways to get rid of that solvent signal, even if it's there, but it's just easier if you don't have to do that. So what are we looking for? Well, you want nicely shimmed peaks. So when you get your sample back out, you want to see that all of your peaks are nice sharp signals, and if it's a singlet, you should see only the one peak, and it should be nice and narrow and symmetrical. So if it's well shimmed, which the gradient shim should do that, you will get nicely shimmed peaks. The other is to think about how concentrated your sample is. If you put your sample into deuterated chloroform, which has a peak at 7.24, and then there's a peak at 0 for the TMS that we add, you should be able to see your peaks at least as tall as that deuterated signal, or else you're not going to have very good signal to noise because you're going to have little tiny peaks. They're hard to interpret. And so another thing to check is just not that you just have solvent, which is a common problem in the organic lab. They don't put enough sample in there, and you get back a solvent, and they say, oh, I have peaks, so it's good. Check the list, because there's a list in there for all our deuterated peaks, or solvents, and it tells you where the solvent peaks are going to show up. So if all you're seeing are two signals, likely all you have is solvent in that. So another thing to double check. When we're looking at carbon NMR, remember that it's only 1% abundance of all of the carbon atoms. So most carbon atoms are carbon 12, 98.9%. 1.1% are going to be carbon 13. So you need lots of samples and or lots of scans. Or lots of samples, not samples. So put in more concentrated sample. Or lots of scans, or both. And we'll be able to see that better. So we're going to look at interpreting carbon 13 NMR first, because it's a little bit simpler, and then we'll move into the the proton NMR. So what are we going to look for? There's really only two things we're going to look for in the carbon. First thing is the number of signals. So you're just going to look across and you're going to identify your solvent pits, and you can get rid of those, and then identify how many of your carbons you are seeing in your NMR. This will give you an idea of the number of carbons, but as we'll look at, you also have to think about the symmetry of the molecule. The next is the location of those signals, and that will be our ppm chemical shift, which we use the lowercase delta to indicate. So only two things. Those things that are not very useful for carbon are going to be our integrations and splitting patterns. So those are things we will look at in addition on the proton NMR, but carbon, they are not very useful. And we'll get into why in a little bit. So what do we mean by the number of signals? Well, here are And these are from SPBS, so our solvent peak is not showing up, probably because they had a very, very concentrated sample. But if these are in chloroform, you would see the peak at 77. I don't really have any examples with that, so I'm going to remind you that if you have that peak at 77, it's actually going to have 3 lines. At 77.0 ppm, and that is going to be your carbon-13 peak, and that is a peak that you can't ignore. And it's very distinctive because they're all the same height, and when we get into NMR, we'll talk about why it's actually a triplet and why it's split. If we look at these, what's that? That's chloroform D, yes. So this would be chloroform D. Some percentage, 1.1% of your chloroform D molecules are actually going to have a C13. Looking at these 2 spectra, we see that there are 1, 2, 3, 4, 5 signals in the top one, and the bottom one has 1, 2, 3, 4, 5, 6, 7, 8 signals. Now, as I said, these are actually very similar molecules. One of them is a para-substituted molecule, and one of them is a meta-substituted molecule. Have para-methylbenzaldehyde or meta-methylbenzaldehyde. These give us different numbers of peaks on the NMR. This is because we have to look at the symmetry of the molecule. If we look at para-methyl, we could draw a line down that, and this half of the molecule is exactly the same as this half, and so they are going to show up as the same signal because they are in the same chemical environment, like we said. And then we would have one here for our carbonyl. We have one signal there. One here. Another one for, these ones are the same though. And then we have 5 and 6. None of that fancy inorganic symmetry. We're just looking at easy planes.
3 dimensions.
So if you have a plane there, you could also have a couple planes if you then a molecule like this. So each of these are going to be exactly the same because they're each next to one of the methyl groups. You're also going to see these ones all the same because they are a carbon of an aromatic ring directly attached to the methyl group, and then one more set of signals, which would give us 3 different signals on the NMR.
How does it give 3 different instead of 2?
These ones are different than that one, and then those 2 are different. One has a methyl group, one has a hydrogen.
The 2 like bottom like things though are the design.
These are the same,
Oh, okay.
as is that one. All 3 of those are the same. All 3 of these are the same, and all 3 of these are the same. But we have 3 different kinds of total. Did you have a question? Okay. So we have 6 signals. Is that how many I counted? No.
Counted 5 on the top.
But note that this one is rather tall. I think they're showing up in the same place. Unfortunately, makes it difficult. That's the other thing, they can have accidental accidental alignment of the two peaks that puts them in the same place as well. The other spectrum here, I did count 8 before, right? It has 1, 2, 3, 4, 5, 6, 7, 8 different carbons, and we see each of those different carbons because there is no symmetry. If you're trying, oh, Brandon.
Is that methyl group on the metal? Meta.
Oh, sorry, yes, it's supposed to be an aldehyde. Thank you. Okay, now there's no symmetry in that molecule. If you're trying to decide if a molecule, or if two carbons or hydrogens are the same, you have to look at start looking at what its neighbors are, see if they're in the exact same environment, but it really has to be the exact same all the way out across the structure. So if you see any differences, then you can't say that they are the same. But in some instances, they may show up in the same place. That's not how we would predict it. Sheldon.
So for the second one, there's 8 signals for each of the carbons that you detect.
Yes.
On the first one, we have 6 and we have 5 signals.
I think it's because this one is actually 2 of them. It's 2 signals that are coming real close together or right on top of each other. And the SPBS you can't zoom in on their spectra very well, so it's hard to tell, but we'll see an example of that later. Okay, so we've got the number of signals based on symmetry, and then we have the location of those signals for our interpretation. And here is the very basic scale, and it all depends on your electron density around that atom. So your alkanes are going to be what we call the most shielded. So they are going to be the most confusingly upfield, because 0 is upfield, 200 is downfield. So our alkanes are most shielded. They have nothing pulling electron density away from them. As we add halogens or oxygens, you start de-shielding the carbons. Double bonds de-shield even more, or triple bonds, so our alkanes, and then our alkenes. Note that these kind of overlap between the alkenes of an aromatic ring and an isolated alkene. And then our carbonyls end up at the most downfield because they are the least shielded out of all of them. So here we have 1, 2, 3, 4, 5, 6, 7 peaks. One of them is pretty shielded, right in the range of where we would put alkane type peaks. And then the others are showing up in our region between 100 and 160-ish, which are all of our alkene aromatic type region. So this molecule is same molecule we kept looking at in the mass spec section, where we had the orthocresol. The methyl group is the one showing up at around 20. We have A, B, C, D, E, F, G. A is going to be this methyl group here around 20 for the alkane region. B through G are all going to be within our aromatic region. but one of them is pretty significantly shifted from the others. It's shifted up to about 155. Which one of those do you think is going to be the one that's going to be shifted to 155?
G.
Oh, that was quick. Alright. We have the aromatic ring that shifts it, but then we also have a OH group that's shifting it further downfield than the standard aromatics. And we can distinguish that one. The other ones are fairly similar. You can tell a little bit by their height. So the shorter of the peaks, shorter peaks tend to be, in carbon, tend to be ones that are not attached to a hydrogen. So I would surmise that that would be B. The other ones, we would probably have to go through and assign with more in-depth table. But we can just say that the rest of these are E, C, and F and D. In no particular order, apparently. Those are the ones that are left over. Now there are more in-depth tables that you probably saw in OChem 2, and there's a much more in-depth table in our textbook that we'll get to. But this will be our basis getting started, is just to remember those general regions of the spectra. Questions on that? Okay. One more technique we talked about in OChem 2 was the depth technique, which looked for different signals in the carbon-13, and it depended on what they were attached to or what hydrogens were attached to each carbon. This helps you then interpret the spectrum more, because that other one didn't tell us much about what was attached to what. This is going to say whether it's a CH3, a CH2, a CH, or a just plain carbon with no hydrogens attached. So when you're fully decoupled, you're going to see the CH3, CH2, CH, and the carbon. As you can see there, they're all going to be positive. If we do what's called a depth 90, we change the angle at which we're irradiating, and only the CH groups show up as a positive peak, and we can interpret those. None of the other carbons show up in your depth 90, so if you have a carbon in a depth 90, you know that it is a CH group. Then we do change the angle again to 135, and we get 3 signals. A CH3 and a CH are both going to be positive. And our CH2 is going to show up as negative. Note that the carbon with no hydrogens does not show up in any of the depths. So if you have a signal that's not shown up in any of the depth, then you can assume that it doesn't have a hydrogen attached to it. Now you have to run, if you want to fully distinguish all of them, you would have to run the depth 90 and the depth 135 to distinguish the CH and the CH3, but that would be additional time on the instrument. You may just want to run a normal spectrum and then a depth 135, because that will distinguish at least the CH and the CH3 and the CH2. And then if we get into some fun 2D experiments, you can line all of them. Let's look at an example. So here they did just a depth 35. So you can see that they have positive signals and the negative signals. Sorry, that's not a depth 35, a depth 135. So you have your standard signal, proton decoupled. We're seeing 1, 2, 3, 4, 5, 6 different peaks. And then in the depth signal, this one disappears, so we know that doesn't have any hydrogens attached to it. These two are negatives, so they are CH2s, and then we have three signals that are positive, so they're either CHs or CH3s, and they've actually assigned this out in this structure so you know which ones are which. And you can do that with other techniques, or if you run a depth 90, you would be able to distinguish those two. Questions? Ready for proton? Okay, let's move on. So again, how do proton and carbon-13 differ? So if you remember, 1.1% abundance versus essentially 100% abundance for H1. There's a few implications for this. First is you need a lot more sample. If you're doing a carbon or scans, which we mentioned already. I also mentioned that splitting is not important. We actually get rid of the carbon-proton splitting, because you can do that, but it makes it harder to see the signals. And we don't see carbon-carbon splitting very often, because that would require that you had a C13 next to a C13. If we were to have a sample of 100 molecules, likely each of those are going to have one carbon-13 in them. But the likelihood that two carbon-13s are in the same molecule and happen to be right next to each other is going to be very, very small. And so there's not going to be any signal from splitting between those two. Proton, on the other hand, all of our protons are going to be active in the proton NMR because all of them are H1. And so they are going to interact with one another, and that's what's going to give us our splitting in our spectra. So you're going to have signals where you have a hydrogen neighboring another hydrogen, and they are going to interact with each other. I don't know what just happened. Cooling down. All right. And since they're going to be sitting right next to each other, they're going to affect one another, and that's all we're going to. Or that's what we're going to have to interpret. It also means that we can use less sample because every hydrogen is going to react to our radio waves, and we'll be able to see it. I have to wait for it to cool down and then warm back up again. What are we going to look for in the proton NMR?
Splitting.
Splitting, yes.
Integration.
And integrations.
Location.
And location.
I said that first.
We'll put splitting at the bottom. And that's the last thing we're going to examine. Integration. And our location.
Number
What
of
was number
signals.
Number of signals.
Yeah, same thing. Number of signals. Sometimes we skip over that one because it seems less important, but it is important for our overall interpretation of the spectrum. It's really hard to have spectrum showing. One and four. No, we're going to look at groups of signals. So you've got an individual signal. It may be split, but we'll count that as one signal. And so a triplet we count as one if we're counting the number of signals, because that tells us the number of types of hydrogens that are in the molecule. Now we have to you look for symmetry within your molecule, and that can tell us how many different groups of hydrogens we're going to see. Also remember that if you have a signal where there are more than one hydrogen attached to the same carbon, we're likely going to see that as one signal. Likely. So if this was our signal, or our molecule, we're going to see these each as different groups of hydrogens in the spectrum. So we would see 5 signals in this one. That's if they don't overlap, which my spectrum happens to not overlap because I carefully chose it. So that's not going to be true for all of them. If we're looking at this just in terms of the number of signals, as I mentioned, we're going to count this as one signal, even though it's a doublet, which we'll interpret later. That's one signal, one, and one. So we have 5 signals in this spectrum, which all of these are going to be of the same molecule. Which is this. They're substituted. You can see we have a CH3 group. Those are all going to show up together. Then oxygen and the next carbon over don't have any hydrogens attached to them, so we'll ignore those. These 2, based on symmetry, if you draw a benzene as a hexagon. And these 2 have the same signal. Then we have 2 other groups out here. So we have 5 separate signals in the proton NMR. Remember that there can be carbons that don't have any hydrogens attached to them. How many bonds does carbon make?
4.
4.
Sometimes.
Wait, no. You guys, go back 2 years. No more inorganic. Only if you're doing really crazy things to it.
How many does hydrogen make?
4
1.
bonds.
Sometimes.
Nope, go back to 4. Unless you have a metal in your compound, stick with 4. So that means that these carbons at the ends of your chains here, or not the ends, at the intersection between the oxygen and the aromatic ring, it has 4 bonds to it already, so we're not going to add a hydrogen there. Another brief side note, while you're interpreting spectra, remember your functional groups from OCHEM, and try to draw functional groups that were in our standard set of things. When people start trying to interpret spectrum, they sometimes forget those and start drawing nitrogen-oxygen bonds, which are not very common. So try and remember those so that you can draw reasonable structures, as in underlined on the worksheet that you had. Okay, so 5 signals in this one. What about the location? So another kind of cartoon here. Again, upfield being 0, downfield being 10 to 12. So an alkane is going to show up around 1 to 2. If you put it next to a carbonyl or a double bond or an aromatic ring, you're going to get up to 2 or 3. If we put a halogen or an oxygen, you're, again, removing electron density. And this depends on the electron density. So 3 to 5 approximately, your halogen, oxygen. These are all ranges though, things move in and out of those ranges, but they're approximate. Most compounds are going to show up within that. The alkenes tend to be between 5 and 6, and then your aromatics between 7 and 8. If you have any aldehyde hydrogens, they will show up between 9 and 10, or a carboxylic acid up 10 to 11. at the general ranges of these, here we have two signals around 7 to 8. These are going to be our aromatic signals in our structure. So these two signals are aromatics, so they're going to show up between 7 and 8 ppm, or close to there. We have one signal next to the oxygen, so that's going to show up between 3 to 4 ppm. Oh, and that got cut off on here because I didn't have enough room, but this is the ppm scale. The next signal over here is next to the aromatic ring, so it's slightly deshielded. But it's going to show between 2 and 3. And then our methyl group, not very deshielded, is going to show up between 1 and 2 ppm. So we have our 5 signals. We have approximate locations. If we line these up, these were between 7 and 8. Our methyl was right around 3.8, so between 3 and 4. Our one next to the aromatic ring, slightly deshielded, around 3. And then we have our last signal around 1 for that methyl group. Again, nicely spaced. How do we interpret the intensity of the signal? This is our integration. Integration meaning the area under the peak. That's going to correspond to the number of hydrogens for each signal. So using my two sources of spectra, SDBS does not put any integration on their spectra, although if you draw in the molecule, you should be able to, or they draw in the molecule and then sign all the peaks, so you should be able to tell how many each of them are. Sigma Aldrich draws in this curve, which looks somewhat similar to the ones you're going to get out of the Delta program, except yours are just going to be truncated here to here, here to here, and they all normalize to the bottom of the page. But it gives you the same information, although Delta gives you a number associated with that as well, which is a little easier to interpret. So when we're interpreting this one, we're going to look at the height difference between here and here, and we would measure that out. When I measured this out on my printout, it was 0.7 centimeters. This one was also 0.7 centimeters. This one was 1.1 centimeters. This one is 0.7 centimeters. This one is 1.0 centimeters. So pretty close. These aren't whole numbers though. We need whole numbers, so we would divide by our lowest one. Luckily we only have 2 sets. This is 1.0, not 10. 0.7 divided by 0.7 equals 1, and then 1.1 divided by 0.7 is approximately 3/2. And we still have a fraction, so we need to multiply by 2 to get rid of that fraction. So each of the 0.7 corresponds to 2 hydrogens, and each of the 1.1 or 1.0 are going to be 3 hydrogens. So we have 2 hydrogens here, 2 hydrogens here, 3 hydrogens, 2 hydrogens, and Then D has 2 hydrogens. Oh wait, now I got this wrong. That's not A. That's E. Because it's less shielded, or more shielded. A is this one with the 3 hydrogens. And then for C and B, we have 2 hydrogens that are the same. We go across the ring from symmetry. So we have 2 of each of those. So we can know the number of each signal, or number of hydrogens each of them correlate with, and their location, and then the number of signals. And lastly, we have our splitting patterns. For this one, I've zoomed in on the 2 regions that have splitting, and if you remember the rule, it is n plus 1. N equals the number of neighbors. Let's say neighboring hydrogens. If we look at this peak at 7.9, it is a doublet. So there's 2 signals. Our n plus 1 means that we are looking at 1 neighbor, and that's going to be the one that's right next to it on the aromatic ring. And so this is our hydrogen we're looking at. There is 1 neighbor next to each of those hydrogens, and that splits it into a doublet. And you see 2 signals. Then the peak at 6.9 is the same way. These each have 1 neighbor, and so they are going to be a doublet. The signal at 3.9 is all by itself out here on this oxygen. It has no neighbors, so it is a singlet, showing up as 1 peak. There's the CH2 at 2.9. It is, if you look up there, 4 lines in it, a quartet. And that is because it has these 3 neighbors. So it's 3 neighbors plus 1 gives us 4 for the quartet. And then our signal at 1.2 is going to be called a triplet. It is 3 lines on that signal, and it has the 2 neighbors here. They don't show up as even signals unless they are a singlet or doublet. The singlet, of course, is just 1 line. The doublet is 2 lines that are equal, and that is, we interpret using the Pascal's triangle. So our singlet and our doublet are going to be equal height. The triplet, as we go down, is going to have the middle line be twice as tall as the 2 outer lines, which you can see there is approximately twice as tall as the 2 outer lines. Our quartet is the 1 to 2 to 2 to 1 ratio, and that's the one that we see at around 3. You can see the 2 middle lines are approximately 3 times as large as the outer lines. To do Pascal's triangle, you then add these numbers together. So this is going to be 4, 6, 4, 1, and the quintet going to have a 1 to 4 to 6 to 4 to 1 ratio between all the peaks in the quintet. If you're seeing things that are not following that Pascal's triangle, they are not doing common splitting. And we'll have to interpret those differently. Alright, here's the one we have to interpret. Oh. Eraser. Let me select this.
Impressive.
Got it. So here is a spectrum to interpret. If we look at the carbon NMR first, we have what appears to be 1, 2, 3, 4, 5, 6, 7 signals. This peak right at 77 is our chloroform D.
Why would you, that third one in, why would you count that as one?
That one?
Yeah.
Because it's hard to tell unless we zoom in on it. Which is why I got the zoom in here. It is actually 2 signals. Yep. I was just, yeah, that is actually 2 signals. It's hard to tell unless you're able to zoom in, but that is 2 signals. And so we actually have the 1, 2, 3, 4, 5, 6 signals, and then 2 others. So we have 8 carbons on our structure here. The region here is our aromatic, so we are seeing all 6 of our aromatic groups, carbons, which means there's no symmetry around it. Then we have 2 signals right around 20, 40, so we have 2 more carbons. They're showing up. Whatever they're doing. I don't know yet, right? All we see are 2 carbons that have alkane structure approximately. That's when we go to the proton NMR for interpretation. As we look at the aromatic region, we see 4 signals. 1, 2, 3, 4, which means that we probably have 2 things substituted on our benzene ring. And each of them are equivalent to 1. So we have 4 hydrogens, splitting pattern. Any guesses on what that splitting pattern tells us about where those substituents are?
They're ortho.
They're ortho, right. We've got a doublet. We do have doublets going on here, but that's a little bit finer interpretation. If we look, we have a doublet, triplet, and that gives us an ortho substitution of our 2 things that are attached to it. And because this one's going to be a doublet, this one's going to be a triplet, doublet. What about this one? What type of group gives us this type of signal?
The
1,
quintet.
2, 3, 4, 5, 6, 7. Septet would be the name we would use. 6 neighbors. And then we have the signal at 1.2 that is a doublet, so it has 1 neighbor. What's the integration? This is 1, that's 6. So we are looking at a group that has 1 hydrogen next to 2 carbons that each have 3 hydrogens to add up to our 6. So we have an isopropyl group attached here.
Symmetry. Oh. Symmetry.
What else is attached to this benzene ring now? We're run out of carbons.
Oxygen.
Yeah, it is an oxygen. It shows our deshielding here in the carbon, and then we have an additional 1 hydrogen peak, which is an OH. So we have a phenol on that aromatic ring. We have these 2 carbons here, so there is actually one thing of symmetry, because those 2 only showed up as 1 signal in our carbon NMR here. So we see 8, even though there's 9